Good morning, afternoon, evening, whenever you're doing this. We're going to do lesson 9.2, graphs of polar equations. And so we're going to do some graphs. Really not that difficult, to be honest. Just takes a little time, a little patience. So it says the graphs of polar equations. A polar graph is the set of all points with coordinates r, theta. So remember, r is your radius, and theta is the angle of rotation from the positive x-axis, which is also called the polar axis. So the positive x-axis is equal to the polar axis. And it says it satisfies your given polar equation. The position and shape of polar graphs can be altered by multiplying or adding to either the function or to theta. So these are going to look very much like the trig functions that we had in the past. So the first example says graph the equation r equals 2 cosine 2 theta. And so we actually have a table that's filled out already, and it says make a table of values on the interval from 0 to 360. So basically we're just going around the unit circle and using the angles that we did in our unit circle. And so we start with theta equals 0, then 30, 45, 60, 90, 120, and so forth. So basically what they did was they made a table and they put those angles in for theta. So for instance, when r equals 2 cosine of 2 theta and we let theta be 0, you can plug that into your calculator, and you want to do that when you're in degree mode. And the result is going to be r equals 2 for that. And so that's how they came about our values. So it says graph the ordered pairs and connect with a smooth curve. So what we're going to do is we're going to go around here and we're going to do, okay, our first value is 0, 2, so 0 degrees, and we're going to put a dot there at 2. Then 30 and 1. 45 and 0. So you can see it's kind of looped back already. 60 and negative 1. So when we're on a negative, we're going in the opposite direction. 90 and negative 2. So the opposite direction of the 90-degree angle. 120 and negative 1. 135 and 0. 150 and 1. So you can kind of see what's happened so far. If I were to start connecting the dots, that's what I have so far. Then we have 180 and 2. 110 and 1, 225 and 0. So now we're back at that little loop. 240 and negative 1 would put us right here. 270 and negative 2. 300 and negative 1. 315 and 0. 330 and 1, and then 360 and 2. So I'm going to go back. So we started here, and it took us around, brought us down, and we came here, and boom. Oh, and we finished up like that. So what we have is this flower, basically. You can see that. You can see the middle of it. And this is called, it says this type of curve is called a rose. It says notice the farthest points are 2 units from the pole and the rose has 4 petals. So the farthest point, that's like its maximum value. All right, so that one was in degree measures. And we're going to do another one here in radians, and you can see that I know it's kind of hard to see. You might be able to zoom in a little bit or enlarge it. But we have our angle this time is in radians, and we're given the output, which is our radius. I'm going to change this up just a little bit because it's going to be so small. I'm going to come out here and I'm going to make this 2, okay? 2. And this would be 4 out here, just so we can make it a little bit bigger. And I'm going to plot those points as well. So I have 0, 1. This is my polar axis here. It was labeled as 2 pi, but it's really a 0. It's the same as 0. And then we'll have 0, 1, pi over 6 and 2, pi over 4 and 2.4. Oh. Let me back up. Okay, sorry. So get a little bit easier to see. Sorry, 0 and 1, pi over 6 and 2, pi over 4 and 2.4. So about right there. Pi over 3 and 2.7. Pi over 2 and 3. Two pi over 3 and 2.7. So we're back over here. Three pi over 4 is 2.4. 5 pi over 6 is 2. And pi is 1. So far we have this. And then at 7 pi over 6, we're back to 0. Um, 5 pi over 4 is negative 0.4. So we're going to go the opposite direction. So we'll be right in there. 4 pi over 3 is negative 0.7. 3 pi over 2 is negative 1. And then you can see that it's kind of symmetrical here, or it's very symmetrical. It's not kind of, it is. And then 11 pi over 6 is back at 0. And then we're back at 1. So actually what happens here is it's going to dip below the polar axis just a little bit. There are values between pi and 7 pi over 6. And then it's going to come up here and make that little curve. So you have your graph. And so this is called a limacon. Weird name, but it's true. Okay, so let's look at one more option here. This says classic polar curves. Some things that we need to know. It says the graph of a polar equation is symmetric, so that's important. It's symmetric with respect to the polar axis if it's a function of the cosine theta. So symmetric with the polar axis, remember that's the positive x-axis, if it has a cosine theta in it. Okay. And it's symmetric with the line, or the, excuse me, the line pi over 2 if it has a sine theta in it. And then it says it's symmetric to the pole. So there's a thing called origin symmetry. This is very similar to that. It's symmetric with the pole if replacing r theta with negative r theta, or r and pi plus theta produces an equivalent equation. And so it helps to know this, and then you don't have to plot as many points if you know that it's symmetrical. Kind of like drawing in a parabola. If we know one side, then we know what the other one's going to look like. So I have an equation here, r equals 1/2 sine of 2 theta. And so since there's a sine in it, I'm going to assume that it is going to be symmetrical about the line pi theta equals pi over 2. So we're going to have to go back a little bit and think about graphing this. The first thing we want to do is graph it in rectangular form, and that's going to give us some points there. So think of this as y equals 1/2 sine of 2 theta. If we graph our parent function, y equals sine theta, if you remember what that looks like, it's going to have a 0 at 0, 1 at pi, and 1 at 2 pi, and then I'm going to let this be a 1 and a negative 1. We'll have a max here and a min here, and that would be our function. For this particular problem, our period is going to be divided by 2 because there's a change in the period, and our max, our amplitude, is only going to go to 1/2. So we're going to go from here to here. So that's the period of the function now, which means that in between we'll have max and min. So this is pi over 4, and this is 3 pi over 4. And we're going to go up to 1/2 at that point. And so our actual function looks like this. That's one period of the function. So what we would like to do is do the same thing on the graph. So we have, remember this is 0, so this is our polar axis, and we're going to graph there. Hopefully I can get this all before time runs out. But we have a point at 0, 0. We have a max at pi over 4 of 1/2. I'm just going to let this be 1/2 right here. And let this be 1. And so what happened is it actually would look like this. And then we come back to 0 at pi over 2. Then we have another one that's at 3 pi over 4. We go back to 1/2. Nope. And it's going to come back here. So if we have symmetry along this line, then it should also go from here to here and here to here.